All right, so last lesson we talked about trig substitution and definite integrals. Today's lesson is trig sub with indefinite integrals. So let's go back to the first example from the last lesson, which was the integral of 1/2 root 4 minus x squared dx. Now, of course, in that lesson we had bounds, but since we're talking about indefinite integrals today, we're just gonna not have those. All right, so I'm just going to quickly go through the substitution again. You do have it in the notes, so I'm going to go through this pretty quickly. So yeah, we made the substitution x equals 2 sine theta, so dx is going to be 2 cos theta, and that gives us the integral of 1/2 root 4 minus 4 sine squared theta times 2 cos theta d theta, right? And of course, the 1/2 and the 2 cancel out nicely. And I'll skip a few steps and we'll get straight to here. 2 times the square root of 1 minus sine squared theta, cos theta d theta. And this simplifies again into just the integral of 2 cos squared theta d theta, and which equals cos theta times sine theta plus theta plus c. All right, and from here in our last lesson, what we did was we put in like pi over 2 into this, and then we subtracted the negative pi over 2 into this, and we got an answer. But if we're doing indefinite integrals, we can't just leave this in terms of theta. Let's remember that our original question is in terms of x, right? So how do we get cos theta sine, the bell. Okay, so how do we get cos theta sine theta plus c back into x forms? Well, let's first remember the substitution we made was x equals 2 sine theta. If we quickly rearrange that, we get x over 2 is going to equal sine theta. So we can immediately plug that in there. That's nice. We got sine theta. But what about cos theta? Because we can't really get it out of just that. Or can we? What we have to do is we have to try and squeeze every little bit of information out of this substitution, x equals 2 sine theta, or this slightly easier to work with form, x over 2 equals sine theta. Now, let's remember from basic trigonometry that sine of theta is equal to opposite over hypotenuse, or SOHCAHTOA, right? So if we have x over 2 equals sine theta, then x must be our opposite, and 2 must be our hypotenuse. All right, well, how can we use that information? Well, if we were given a triangle with this information, the triangle would look like this. We have a right triangle, and let's make this angle theta, and we would have the hypotenuse 2 and the opposite x, right? Opposite. Which would make this the adjacent. Now, we don't know the adjacent yet, but we can use the Pythagorean theorem to find it out, right? So if we call this side b, well, a squared plus b squared equals c squared. So if we rewrite that, we will get that b equals the square root of c squared minus a squared, or in this case, just scroll up a bit, b is going to equal root 4 minus x squared. Now, interestingly enough, this radical here on the adjacent side of our triangle is the same radical in our original question. So that's actually a thing that happens every single time you do trig substitution. If you make this triangle and you don't see your original radical on one of these 3 legs, then you have done something wrong. Either the numbers in the triangle are wrong, or the numbers you substituted were wrong, but something is wrong. But in this case, we do have the right thing. So now that we know the adjacent side, which is 4 minus x squared, we can actually solve for cos theta, because cos theta is equal to adjacent over hypotenuse, right? And so that makes cos theta in this case equal to root 4 minus x squared over 2. Okay, that's cool. So now I have cos theta, sine theta, and we just need theta. And let's just go back to this x over 2 equals, let's just go back to this x over 2 equals sine theta again. And you know what, I'll erase some of our work to make this cleaner. All right. The way you have to as I erase, I'll just speak. The way you have to find theta is you need to use arcsine. Now, just remember that arcsine of theta is going to be just theta. So if we take the arcsine, hold on. If we have x over 2 equals sine theta, if we take the arcsine of both sides, we're going to get arcsine of x over 2 equals theta. All right. Well, now we solve for cos theta, we have sine theta, and we have theta. So let's put that all back into our original expression here. And I'm just going to move this off to the side. I'll just move this off to the side so it can work. That did not work. Okay. This lasso tool is more difficult than I thought it'd be. And I'm just gonna. All right. So now let's put our substitutions in. So now what we're going to have is root 4 minus x squared, which replaces cos theta, x over 2 multiplied by x over 2, which replaces sine theta, plus, and it looks like we're going to need a little more room to write, so I'm going to move this one too. That's not. Plus arc sine of x over 2 plus c. Just gonna block this off here. Okay, let's just quickly simplify that. And so now we're gonna have x root 4 minus x squared over 4 plus arc sine of x over 2 plus c, and that's actually going to be our final answer. I know it looks pretty weird, but and you know, you still see something related to sine, you know, arc sine. Wait, I thought we got rid of all of those. But let's just remember that the derivative of arc sine is actually going to be 1 over root 1 minus x squared. So there are some patterns going on here, and if you're welcome to check that. You can take the derivative of this here, and you can check that it equals our question on your own time. I'm not going to do that here. Okay, so this was a sign substitution, right? But actually, there are 2 more forms of trig substitution that we can do this with, and let's go over to them now. So I have a very nice chart here. So the first other form is root a squared plus b squared x squared. All right, and the substitution you make is x equals a over b tan theta. And you do that because the identity you want to use is 1 plus tan squared theta equals secant squared theta. Now, how do we know which identity to use? Here's another one. Secant squared theta minus 1 equals tan squared theta, where you need the form b squared x squared minus a squared. These 3 forms, a squared minus b squared x squared, a squared plus b squared x squared, and b squared x squared minus a squared, they're all very similar. So how do you tell them apart? Well, the way you do it is you look at the identities being used. Our first identity, 1 minus sine squared theta equals cos squared theta. I'll just write it out. This is a constant square minus a variable square. Sine squared theta has a variable, right? That's why the form it lines up with is root a squared, which is a constant, minus b squared x squared, which is a variable square, right? Now, how's that different from this third identity, b squared x squared minus a squared? Well, if we just write out this identity quickly, secant squared theta minus 1 equals tan squared theta, what we have is a variable square minus a constant square. And that's why the corresponding form you substitute for is a variable square, b squared x squared, minus a constant square, that a squared. All right, so that's the difference between those two. And then for the tan one, it's a bit simpler because the substitution where you use tan is the only one with a plus. All right, so obviously the order for that one doesn't matter. You could have 1 plus x squared in the root. You could have x squared plus 1, but because it's plus, it doesn't matter. So yeah, that's the way you figure out exactly which identity you use. So let's try some examples with our newfound trig substitutions. And we'll start with this example here. All right, so it's a bit more complicated. We've got an extra x here, you know. But ultimately, what you want to notice is that you have this form, root a squared plus b squared x squared. Now, of course, in this case, we have a equals 1, b equals 1, and so this is going to be a very simple substitution. We are going to make the substitution x equals tan theta, and dx is going to equal secant squared theta d theta, because secant squared theta is the derivative of tan theta. All right, now let's put that into our integral, and let's see how this goes. So now we have the integral of secant squared theta over, and notice we have an x in the bottom there, so we actually do need to put in tan theta for x down there. So now we have secant squared theta over tan theta root 1 plus tan squared theta, and I'll add the d theta on the very end. Just a quick note: when you see like if you have something like a dx over some function, that's just like writing dx on the side, and there's an invisible 1 here. You could say it's 1 dx, you know, but that's not a big deal. All right, so now we have this integral, and let's begin simplifying it. So now we're gonna have secant squared theta over tan theta, and 1 plus tan squared theta is equal to secant squared theta. So now we have this, and we take the square root of secant squared theta, so our integral now becomes secant squared theta over tan theta secant theta d theta. All right, and let's just remember again that we work with the positive version of secant theta, although typically there should be absolute value signs. We don't really care in this case because we use the positive versions. I won't go over the bounds this time. They are in the chart if you would like to take a look. But for indefinite integrals, you won't really need to state the bounds because you're not working with real like numbers, right? So now I have this. Let's simplify. We can get rid of 1 secant theta on the top and our only secant theta on the bottom. So we're left with the integral of secant theta over, if it will let me scroll, secant theta over tan theta, over tan theta d theta, and this is going to equal, well, secant theta equals 1 over cos theta. So now we could rewrite this integral as 1 over cos theta, and well, tan, if you have tan in the denominator, tan is typically sine over cos, but if you have it in the bottom, then you'll have cos theta over sine theta. All right, and let's notice that cos on the top cancels out with cos on the bottom, so now we're just left with the integral of 1 over sine theta d theta. Okay, this isn't exactly an easy integral to do, but in this class you are provided with a chart of antiderivatives. So 1 over sine theta is equal to cosecant theta. Yes, cosecant theta. And so if you check your chart, you will find that the integral of cosecant theta is just going to be, is it ln? I think it's ln. Yes, it is. It is ln of the absolute value of cosecant theta plus cotan theta plus c. All right, and again, we have to turn this back into x terms because our original question was in x terms. So let's remember that the substitution we made was x equals tan theta. If we want to help ourselves, we could write it as x over 1 equals tan theta, right? And now we can see, since tan theta is equal to opposite over adjacent, we have this x here is going to be our opposite, while 1 is going to be our adjacent. So if we draw out our triangle, we'll save that question for later. So if we draw out our triangle, it should look like this. We got the right angles here. You know what? That's a pretty ugly triangle. Let me restart. I don't know if that's better. Ugh. Okay. I mean, you could set up the triangle any which way with the right angle here, theta here. It doesn't really matter, but this is the easiest way to do it, and so this is the way I'm going to do it every single time. Once you start doing it this way, there's really no reason for you to do it a different way. All right, so back to the thing. So this is our opposite side here, so x is going to go here. This side is our adjacent, so 1 is going to go here. And now by the Pythagorean theorem, a squared plus b squared equals c squared. So this c side is going to just be, it's going to be root a squared plus b squared, which in this case is going to be root 1 squared plus x squared. 1 squared is just 1, right? So we have this. And again, let's notice that this radical is in our original question. It is, right? It's right here. So again, very important that you do see your radical on that triangle, because it means you're doing something right. Okay, so what do we need? We need cosecant and we need cotan. Well, cotan is nice. Cotan is just going to be, cotan is inverse tan, right? 1 over tan. So if tan is equal to x over 1, then cotan should simply be 1 over x. Oh, cotan theta. Cosecant is a bit trickier though. Cosecant is 1 over sine theta, right? So if sine theta is equal, you know what? Let's use a different color for some color coding. If sine theta is equal to opposite over hypotenuse, then cosecant theta must be hypotenuse over opposite. Or in this case, our hypotenuse is 1 plus x squared and our opposite are x. So in our specific case, we have cosecant theta is going to equal root 1 plus x squared over x. All right. Now let's clean it up a bit. Let's clean it up a bit so we can finish this once and for all. Just going to erase some of this so we have a cleaner workspace. All right, so what do we say? So we said 1 over x is equal to cotan theta. We said root 1 plus x squared over x is equal to cosecant theta. And finally, we need theta. We forgot to solve for theta. Or usually we need theta. Actually, in this case, we don't. So that's nice. But if we did, let's say we just had theta alone, then we would use arctan, right? Because we have x equals tan theta. You take the arctan of both sides, you get arctan of x equals theta, and so on and so forth. But let's substitute this in. So now we have ln of the absolute value of cosecant theta, which is root 1 plus x squared over x, plus cotan of theta, which is just 1 over x, and then plus c. Let's simplify that once. We get 1 plus root 1 plus x squared over x plus c, and that should be our final answer, unless I wrote the antiderivative wrong. Hold on, how do you pause this again? Control-Alt-P. All right, so as it turns out, I wrote the antiderivative of cosecant theta wrong. It is cosecant theta minus cotan theta, which is going to change our answer just a little bit. So now we have the root 1 plus x squared over x minus 1 over x. So on this side, we're going to write it as negative 1 plus. And I wrote it as negative 1 plus root 1 plus x squared instead of root 1 plus x squared minus 1, just because I don't want any confusion on where the radical stops and if this negative 1 is included or anything. But yeah, so this is our final answer here. Ln of the absolute value of, you know what? I'm going to circle it in a different color, just because I can. So yeah, so we have ln of the absolute value of negative 1 plus root 1 plus x squared all over x plus c. And again, you are welcome to check that on your program crashed. And it took away my box. Oh, that's no fun. But you know what? It gives me a chance to make a better one. That's not better. All right, yeah, so ln of the absolute value of negative 1 plus root 1 plus x squared all over x plus c. And again, if you don't believe me, you are welcome to check that on your own time. Of course, taking the derivative of it is much easier than integral, so, you know, if you've got spare time on your hands, you can try that. Anyway, so now we have the integral of 1 minus root x squared minus 36. Now, let's remember our thing about the forms. We've got a squared variable minus a squared constant, because 36 is simply equal to 6 squared. Okay, cool. That means, well, what if we just remember the secant identity? We have secant squared theta minus 1 equals tan squared theta, right? We've got the same setup. We got variable minus constant. Okay, so that tells us that this is the right substitution to make. We should make the substitution x. It's going to be x equals a over b secant theta, which in this case, our b value is actually, b is always the coefficient on the x, just for future reference, and a is always going to be the constant. So even though b and a have switched places from when they normally do, right? Because b is here and a is here instead of the other way around, it is still a over b. So b looks like to be just 1, but as we said earlier, 36 is equal to 6 squared, so a is going to be 6. So now we have the substitution x equals 6 secant theta. Okay, and now let's find our dx. dx is going to be a over b, whatever the derivative of secant is. And so it's going to be 6 secant theta tan theta. Oh, that is not how you spell secant. Secant theta tan theta. Because the derivative of secant theta is secant theta tan theta. Oh, that is the homework assignment. How about we move that so we have some more space to write? That'd be good. Let us just... All right, that should be plenty. We'll put that down there. We'll get to that in a second. All right, so now let's put our substitution in. Let's see what we get. So let me scroll down a bit. Jeez. You know what? Let's give this. I want to be able to see the original integrals while we work, so I'm gonna just move this over a little bit, just up a little bit, and maybe off to the side too. All right, this gives us some space to work with. All right, so now our new integral is going to be 6 forgot the d theta on the end. I'm really all over the place. All right, so now we're going to have 6 secant theta tan theta over root, and this is going to be 36 secant squared theta, because remember, our x is not just secant theta, it is 6 secant theta, so we have to square all that. So we have 36 secant squared theta minus 36, and just add a d theta on the end. All right, let's begin our simplification. All right, well, we can factor our radical a few times actually, because first we can take out a 36 and we get secant squared theta minus 1, but we can also take that 36 out of the radical. So this is actually going to become the integral of 6 secant theta tan theta over 6 root secant squared theta minus 1. Because when you take something out from the radical, it becomes its square root, right? That's just something. That's just one of those rules. Okay. So 6 secant theta tan theta over 6 root secant squared theta minus 1 d theta. Oh, don't forget the d theta at the end, because, you know, integral's incomplete without it, without that infinitesimal change. Okay, and secant squared theta, as we said earlier, is equal to tan squared theta, and a square root of tan squared theta is going to be just tan theta. And again, we're only using the positive versions because of the bounds we talked about. Again, if you want to know the bounds for this specific substitution, you may check the chart. But again, definite and indefinite integrals, we're not really going to worry about that sort of thing. So let's simplify this integral one more time, and we're going to get, okay, let's see, 6's cancels out. We have a tan theta here that's going to cancel out with this entire thing, because as we said, you know, why did I erase that? As we said earlier, tan theta. All right, and so now we're just going to have the integral of secant, oh, wow, that is not how you write secant. Integral of secant theta d theta. Okay, again, this isn't exactly a simple integral, although it looks really simple, but it is on your integral chart, so I actually have to check this myself because I don't remember it off the top of my head. But it does look like it's going to be ln of the absolute value of secant theta plus tan theta. I am going to just Google search that. Oh, plus c. I am going to Google search that just because I got it wrong last time. All right, so it is indeed ln of the absolute value of secant theta plus tan theta plus c. So looks like we should be good this time. Oh, this pesky homework keeps showing up. I don't want to give that out yet. Obviously, you can't do some of them yet because we haven't finished this question. Or maybe you can do them. You know what? If you guys managed to pause it earlier and you want to try the homework without actually going through the lesson, you're welcome to do so. I'm gonna keep working. All right, so ln of the absolute value of secant theta plus tan theta plus c. And again, we're gonna follow the same sort of pattern we did with our other ones, where we just remember that our substitution was x equals secant theta, and secant is I'll just write that out. And secant theta is actually going to be adjacent over, or not adjacent, apologies, hypotenuse over adjacent, right? And so if x equals secant theta, or again, we can write this as x over 1. If x over 1 equals secant theta, then, all right, well, first of all, we already have this here. That's nice. But that means x is going to be our hypotenuse, and 1 is going to be our adjacent side. And you know what? I'll draw the triangle in here, just so I don't have to erase. Oh, that is not what a right triangle looks like. This is why I'm majoring in art. No. This is why I'm not majoring in an art-based program. Yikes. Okay, we're just going to say that's a right triangle. I know it's not a right triangle. It looks like a deformed Dorito, but we're not going to worry about that. secant theta equals, yeah, so x is our hypotenuse and a, our adjacent, is going to be 1. Okay, and how do we solve for this last side, our opposite side? Well, we use the Pythagorean theorem. It's going to be root the hypotenuse squared minus the adjacent squared. So it's going to be root x squared. Or actually, what on earth have I done? I just completely forgot our substitution was 6 secant theta. So secant theta is actually, oh, that's awkward. So actually, okay. If you have already written this down in your notes, I'm sorry. It looks like you're going to have to do a bit of erasing. Although if you did it in pen, I have no sympathy for you because you shouldn't be doing math in pen. So actually x over 6 equals secant theta. All right, and so this side here should actually be 6. See, it's nice we caught that, because when we write out the adjacent side, if I wrote it out with 1, I would have gone just root x squared minus 1. And if we just think about it, right, that was not what our original radical was. Our original radical was root x squared minus 36. So because I wrote out the triangle, and because I knew that this root x squared whatever, this opposite side, had to be found in my original question, I realized that my substitution was wrong, or at least I wrote it down wrong the second time. So it's very important that you check this triangle and that you remember that that one of the legs of your triangle, one of them will have your original radical in them. All right, you know, even I make mistakes, a lot of them. Okay, anyway. So from this triangle, we can get that we need tan, and tan is opposite over adjacent. So if given this funky triangle here, our opposite side is root x squared over 36, and our adjacent side is 6. So we have root x squared minus 36 over 6 equals tan theta, opposite over adjacent. All right, and with this knowledge, we are going to, whoa, did not mean to move that far. We're going to put it back into our antiderivative. So now we're going to have the ln of the absolute value of x over 6 plus root x squared minus 36 all over 6 plus c. And of course we can simplify that once if we want, because we got a common denominator in that ln function. So we got ln of the absolute value of x plus root x squared minus 36 over 6, and close bracket plus c. There we go, and that is our final answer. I don't believe there's more simplification to be done. Again, you may check this on your own time. It will be time consuming. It's a lot of algebra. Or you can use Desmos, actually. Yeah, this is a good time for me to talk about Desmos while I move on to the next thing. Desmos, you can like graph like derivatives and integrals and stuff on Desmos, and so you can easily check your algebra with Desmos just by like typing in a function and then typing in a function that's supposed to equal your first function, and you know, if the graphs are different, then you've done something wrong. So yeah, so we did our secant example, secant substitution example, we did a tan substitution example, we did a sine substitution example, and that is going to be it for examples today. I will now give the homework, which is just here. We have these 3 questions. Yes, it's only 3 questions. They will take you some time. There are the answers here too. You may copy those down to check your work. And we have from the Stewart textbook, the red textbook, page 519, number 2A and 5. These ones are a bit more challenging, and they may require like a bit more algebraic manipulation than you've seen so far. They also tie into our lesson 3, which is going to be trig substitution with other methods, but we're not going to worry about that now. Anyway, I will end my lesson here. Mr. Maxwell has gone off to, I don't know actually. He was eating lunch a minute before, but okay. Anyway, I will end it here. Just remember, if we're going to do math well, and don't write math like me. Don't write it in pen, and use Desmos. This is Josiah, and I am stopping the recording.